Hi guys, I'm Lauren Smith and I'm studying theoretical physics in Trinity. I'll be taking you through to 2019's higher level question 3. Today's experiment question is to determine the specific latent heat of fusion of ice. So, let's go. Okay, so here's the first look at our question 3, in which we are going to be looking at the experiment to determine the specific latent heat of fusion of ice. So we're told that the student first crushed some ice and then dried the melting ice before adding it to warm water in an insulated copper calorimeter. And we are given the following bits of data, which will be very, very handy indeed in the calculations part of this question. So let's start answering the questions we're given. Okay, so first off, we're asked, why did the student crush the ice and then dry the ice? So for part 1, why did they crush the ice? The reason is that the ice is all at the same temperature, which is 0 degrees Celsius. You could also put down that the ice would melt faster and that it would give a greater surface area. So explaining all this, say if we had large lumps of ice, these large lumps could have temperature variations, as the lumps would be very, very cold in the center, and as you got nearer to the surface, you'd have a higher temperature. So smaller fragments of ice were better for a constant temperature with their overall greater surface area. And this would allow it to melt faster. If we had smaller chunks, they would melt quicker. Therefore, less time wasted having all this heat being lost to the surroundings or heat given from the surroundings. Any of these answers would give you 3 marks. Okay, so for part 2, why did we dry the ice? And we did this to ensure that only ice and not water was added to the calorimeter. And I just wanted to mention here in my answer that that is what the formula assumes, i.e. the heat formulas, which we will be looking at later on in the question if you stay tuned. So why is this? Dry ice means that there's no condensation, i.e. no liquid water floating around. And this is what is assumed in the formula, as we know. There's no extra weight being added by this liquid water. It's just all ice. Okay, getting on to a more simpler question. How was the ice crushed and then dried? Well, the ice was crushed with an ice crusher. Remember, in your answer, include the apparatus as well as the action. This can really, really help structure your answer. That gives you 3 marks. And how was it dried? It was dried with a cloth or a towel to absorb all of that extra condensation. That will also get you 3 marks. Okay, so now we're asked, why did she use warm water and use melting ice? Okay, so looking at part 5, she used warm water because the ice would melt quicker, aiming for heat loss equals to heat gained to the system. So no heat loss from the surroundings or no heat gained from the surroundings. Ice will melt slowly if the water is too cold, which then allows time for heat to enter in from the surroundings, giving distortions to our calculations, which we do not want. This explanation will get you 3 marks. For your other 3 marks, you have to explain that you use melting ice to ensure that ice is always at 0 degrees Celsius. That gets you 3 marks. And as the melting point of ice is at 0 degrees Celsius, melting ice is guaranteed at this temperature. Okay, so before we dive into the next part of our question, I just want to draw your attention to page 58 of the Formula Tables book, in which we will be using the 2 formulas up here and here. The first one being the energy temperature and the second one being the energy needed to change state of a given mass of substance. Okay, so what is the question asking us? It is asking us to use all the data which they have provided us to calculate the specific latent heat of fusion of ice, which I'm going to denote as L sub ice, just to make it explicitly clear when we're using the formulas what we're actually looking for. Okay, so what formulas do we use? Well, we're going to use the 2 formulas which I stated when we were looking at the Formula Tables book earlier. And it's very important that you jot these 2 formulas down in your answer booklet, because you will pick up marks. Again, another reason why it is so important to always, always, always put down the formulas you use in your answer. Because automatically, if you explicitly write either one of these formulas down, you're going to pick up your first 3 marks. Okay, so in using these formulas, we're going to have to calculate all of the masses of the substances in questions and as well as their temperature changes. Okay, so what masses are we looking for? We're looking for the mass of the ice that we're putting in. We're going to look for the mass of the water, and we're going to look for the mass of the calorimeter. Well, we know the mass of the calorimeter is 56.3 grams, and we're going to need this to calculate the mass of the water and the mass of the ice specifically. Okay, so the mass of the water is equal to the mass of the calorimeter plus the water minus the mass of the calorimeter. And this calorimeter plus water figure does not include the ice at all. And this just gives us 108.5 grams minus 56.3 grams, which is just going to give us the mass of the water to be 52.2 grams. And just by calculating this value here, you're going to pick up another 3 marks. Okay, so let's find out what is the mass of the ice. Well, that's just equal to the mass of the calorimeter plus the water plus the ice minus the mass of the calorimeter plus the water, which is just going to give us 122.9 grams minus 108.5 grams, and that's just giving us the mass of the ice to be 14.4 grams. Now, as you can see, I've calculated all these masses in grams first, and now I'm going to convert them into their SI units, i.e. kilograms. And that would be an exam tip for all of you. When you're doing these types of questions, calculate the masses first and then convert them into SI units. It just makes your life a lot easier, because once you convert them into kilograms, you're going to be working with smaller figures with a lot more decimal places. So therefore, you're less inclined to make any mistakes doing it this way. And therefore, when you divide by 1,000, you're just going to get these values up here as your masses for each of the different substances we're using. Okay, so we calculate all the masses. We're going to have to calculate the temperature changes in the substances that gain heat energy and also lose heat energy. Okay, so we're looking at the temperature change for the ice. Now, the ice itself is gaining temperature, so we're going to subtract the initial temperature of the ice, which is at 0 degrees because it is melting ice, therefore it is 0 degrees, from the final temperature of the ice. So the final temperature of the ice is 8 degrees Celsius. Taking away the initial temperature of the ice, which is 0 degrees Celsius, gives us an overall change in temperature value for the ice of 8 degrees Celsius or Kelvin. And the reason why I put it's a temperature change of Celsius or Kelvin is because we're looking at temperature differences here. And since Kelvin and Celsius temperature scales only differ by one constant, which is 273.15, therefore a change in temperature range in the Celsius scale is equal to the change in the temperature range in the Kelvin scale. So therefore you don't need to convert this into Kelvin or anything like that, because it all just works out the same. Now, looking at the change in temperature for the water or for the calorimeter, they're both the same because they're both losing heat energy and they were both started at the same temperature. We're going to have to take the final temperature value from the initial temperature value, i.e. we're going to have this difference of 29.5 and 8 degrees Celsius, which just gives us an overall difference in temperature value of 21.5 degrees Celsius or Kelvin. Now, calculating the temperature change for the ice gives us 3 marks. Calculating the temperature change for the water and for the calorimeter also gives us another 3 marks. Which is great because just with these simple calculations, we've bundled up already 12 marks out of a possible 18. So already you've passed this section of the question very, very well. Now, how do we put all these figures into practice and how do we calculate the specific latent heat diffusion of ice? As you know from your study of heat, we know that in this experiment that heat lost by the warm water and the calorimeter is equal to the heat gained by the crushed ice. So we can put together a formula. This is it in words and we can translate it into our mathematical equations, which we've looked at above. So we're going to have here on the left hand side for the heat lost by the warm water and the calorimeter. And by the way, just to mention, this formula up here, this word formula up here, assumes that no heat is lost to the surroundings. So it's all kept together in this one little system. We have our first term on the left-hand side is the energy needed to decrease the temperature of the water by 21.5 degrees Celsius. or Kelvin equivalently. I just put in Celsius here just for convenience. The second term is the energy needed to decrease the temperature of the calorimeter by the same amount. All this energy lost by the water in the calorimeter is equal to the energy gained by the ice. So our first term on the right hand side is a very important term. This is the energy needed to change the state of the ice into its liquid form, water. So we're going to use that formula, which we looked at previously. And the second term on the right hand side is the energy needed to increase the temperature of the ice water by 8 degrees Celsius, or again Kelvin. So this is the formula. Now all we have to do is just sub in our figures and we are ready to go. Okay, so here is the formula which we're going to look at, and all we need to do is sub in all of our values here. And by the way, we are given the specific heat capacity of water and of the calorimeter as well. And bearing in mind that we are going to use the specific heat capacity for water when we're talking about the mass of the ice, because at this stage, the mass of the ice for its increase in temperature change has already converted into water. So we'll be using that value for the specific heat capacity. Okay, so let's sub in our values. Okay, so we subbed everything in except for, of course, our target variable, which is the latent heat of fusion of ice. And all we have to do is calculate our values. Now, by the way, just substituting everything into the formula will get you your next 3 marks, giving us a total of 15 out of 18 now. So let's put these into our calculator. Calculating the right hand side, and I would do this term by term. We're given 4691.214 for this term here, and for the second term, let's take out our calculator again. Just multiplying everything using brackets. I find that the easiest in exam. And we're given 472 roughly. And I'd also, by the way, encourage you to write down all of your values instead of just quickly calculating them in the calculator and putting one big final figure down on the page. I'd write down everything step by step. Say if you make a calculator error, it'll be easier for the examiner to know that your mistake was from a calculator error rather than an error in your understanding. We can leave that term on the right hand side as it is, and let's calculate the final term. Now putting this into our calculator, let's hit that equal sign, and we're given roughly 481.5. Okay, so let's just bring all of these numerical figures to one side, including this one over here, and get this target variable on its own. Okay, so we're given that 0.0144 times the specific latent heat of fusion of ice is equal to this figure here. Let's divide both sides by the coefficient in front of the latent heat of fusion of ice to get our final value for L. Okay, so we have the calculator up on screen. We have our final value here, which is stored as an answer, so we don't need to re-put that in. We're going to divide it by this value, and we're going to get this out, which is, when we put it into scientific notation, 3.25 times 10 to the power of 5 joules per kilogram. Remember, do not forget your unit, you will lose marks. And this value is correct and will give you your final 3 marks, 18 out of 18. And on to the final bit of our question, we are asked, why could using a very large mass of water lead to a less accurate result in this experiment? And you have 2 options here which are accepted in the marking schemes. I'm going to give you both. Well, the first one is that the water would have a smaller temperature change overall, as you would need a lot more energy to change the temperature of a larger mass of water, therefore leading to less accurate results, as we know. Or there's another option. There's a greater percentage error in the experiment. There is more heat loss to the surroundings and a smaller temperature change. This means that there is a greater possibility of incorrect measurement. Key phrase here is that there's more heat loss to the surroundings for a smaller temperature change. Either one of these answers will get you your final 4 marks.